This video is going to introduce you to a rational number. Now, technically you already know what they are, a fraction or a decimal. The first thing that we're going to do is put them into context of some of the other number systems that we've been talking about. So most of the numbers that we deal with are what's called real numbers. They represent the big box here. Now within those real numbers, what we have are rational numbers, which is represented by a Q. And we also have irrational numbers, which is represented by a Q with a bar over top. We don't need to worry too much about irrational numbers. Okay, we'll go back to those in a minute. Within our rational number set, we have some more subsets that we've been talking about. So we have our integer number set. Within our integers, we have our whole numbers. And within our whole numbers, we have our natural numbers that sort of started off our whole thing. So if you remember, natural numbers are 1, 2, 3, etc. Whole numbers are the same, except they start at 0. Integers include negative numbers. And rational numbers include numbers like minus 2.5, 1.7, 4 over 5, and everything in between. Irrational numbers are just really numbers that aren't rationals. Some examples of those are pi, or the number e, which is approximately 2.71. It repeats indefinitely. Or the square root of 2 is also irrational. So let's take a look at what the difference between rational and irrational is. This is just a diagram to show you how everything fits together. So rational numbers are fractions or decimals. And in order for a fraction or a decimal to consider it rational, the decimal either terminates or ends, something like 2.5 or minus 1.72, or it can repeat indefinitely with a pattern. So something like 1.333 repeating. The period refers to the portion of the decimal number that repeats, and the length of the period refers to the number of digits that actually repeat. So we'll do some examples of that before we move on. So here are the following rational numbers. We're going to write them as decimals and then state the period and the length. So 2/5, we can find that out as a decimal by doing 2 divided by 5, and this is going to give us 0.4. So this fits into category 1. This is a decimal that terminates, so there's no need to talk about the period or the length of the period because it doesn't really have one. Now let's look at the next example. So minus 3 divided by 8 also gives us minus 0.35. So again, terminates, no need to quantify the period. And then finally, we've got minus 3 divided by minus 11, which is going to give us 0.272727 on and on. So here, our period is going to be the numbers that actually repeat. So that's the 2 and the 7. And the length of the period is 2. When I represent that my decimal repeats, I put my bar over the period or over the decimals that repeat. We also have irrational numbers, which are just defined as numbers that aren't rational or numbers that don't fit the above pattern. We can define the set of rational numbers in set builder notation as Q, so our sign for rational numbers, is equal to A over B such that A and B are elements of our integer number set and B is not equal to 0. So what that means is Q is a ratio of one number to another number. Those numbers have to be integers and our bottom number can't be 0. We can also move on to demonstrate rational numbers in equivalent form. It does not matter where you put the minus sign, whether it's in line with the fraction line, whether it's on the numerator, or whether it's with the denominator. So the convention is that we like to represent them with a positive denominator. So one of these two ways here. So let's practice that below. Here we're going to express each rational number in lowest terms and with a positive denominator. So here we've got minus 3 over 5. That is in lowest terms and our denominator is positive, so that one is complete. In our next one here, I'm going to move my negative to the top so that the denominator is positive. And I'm going to start by dividing the top and the bottom by 5. So 125 divided by 5 is going to give me 25. And 50 divided by 5 is going to give me 10. I can continue dividing here by 5 again. So I get minus 5 over 2 as my final answer. For C, here I notice I've got a double sign. I'm just going to rewrite that with one positive. And then I'm going to simplify my fraction. 56 divided by 7 is just 8. Finally, I've got minus 60 over 100. So my denominator is positive. That is a check. Now I want to divide top and the bottom by 10 to reduce that. So I've got minus 6 over 10. I see that they're both even. I can reduce them a little bit further to minus 3/5. With rational numbers, you should also be able to write them as a mixed number. It's important to note that the sign doesn't change throughout this process. All you're doing is changing the format of the fraction part, not the sign. To write as a mixed number, you need to figure out how many times 4 goes into 13, 4, 8, 12, 3 times. I have 1 left over, which means that I have 1/4 left. You could also do this if you remember good old long division. 4 goes into 13 3 times with a remainder of 1. That tells me what's left over in my fraction. Let's try another example here. I started off with a negative, so my final answer is still going to be negative. Now I need to figure out how many times 3 goes into 11. So counting up by 3s, 3, 6, 9. I get 3 wholes, and then I've got 2/3 left over. You should also be able to go the other way and write a rational number as an improper fraction. Just like in example 3, the sign doesn't change through this part, it's just the fractional component. So the first thing that I'm going to do is take the whole number and multiply it by the denominator, and then I'm going to add the numerator. 6 times 2 is 12, plus 1 is 13, and then I'm going to divide by 2. You could also do that in a visual format by coloring in the number of pie slices you have. So I know I have 6 wholes, 1, 2, 3, 4, 5, 6. And then I've got a half. So I would have 1/2 of my final pie colored in, and then I would have 2 halves of each of my other pies colored in. And then I would just count the number of halves that I have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, which gives me my final answer here. Let's try one more example. Whole number times the bottom, 2 times 7 is 14, plus 4 is 18 over 7. The final thing that you should be able to do is to compare rational numbers. So let's place some examples on the number line below. So the first one is 1/2. Do that in blue. So I've got 1/2. I will go right about here. 3/5. I'll do that one in red. Now 3/5 as a decimal is about 0.6. So I know that's going to be a little bit greater than 1/2. My next one, I'm doing green. Now I've got minus 3/5. So now I know I'm a little bit further than minus 1/2, but still not quite at -1. And the last one that I'll do in yellow here, I've got minus 3 over 2, which as a decimal is the same as minus 1.5. So I can put that right here in between the 1 and the 2. Now we're going to compare some without using the number line as our last example. Before you can compare them, it is helpful to put them into a common denominator. What you might notice here is that this one is less than 1, okay, or closer to 0. It's less than -1. This one is greater than -1. I have an improper fraction. So that means that the smaller negative number has to be larger. It is closer to 0. Now let's look at this number. So we've got a -5 on the top and we've got a -5 on the bottom. So those are really the same. I can rewrite them up here. Okay. And just like before in my first example, I can see that this one on the left is actually closer to 0. So it's greater than -1 because the fractional part is not an improper fraction. Oh, and I switched it automatically. So let's make sure we're copying it down correctly. So we've got -3 over 5 here. This is an example where you do need to change it into a common denominator. So I'm going to change them into both out of 35. So I would have -25 over 35 and then -21 over 35. So what I can see is that -21 is going to be the smaller negative number. So this is actually the larger rational number. It is more positive. It is closer to 0. The last one that we have is a bit of a trick question. I want to get them to the same common denominator, just like I did in example B. But here I can reduce this one to be equal to 1/2. So that means that I actually have equivalent fractions. So just to recap, you should be comfortable deciding whether a number is rational or not. You should be comfortable expressing a rational number in lowest terms. You should be comfortable switching from a mixed number to an improper fraction and an improper fraction to a mixed number. And finally, you should be comfortable comparing rational numbers.